Hello everyone, welcome to the next lecture. We are still very much in the realm of regular languages and regular expressions. Today we are doing some examples. So we are gonna construct a few regular expressions for some regular languages. Should be fun. Okay, let's begin. Today, as I said, we are getting our hands dirty, so I brought back the good old blackboard, which is green. So this is our first example here. We have L as a language, and the definition of L is the set of all binary strings. So the question is L a regular language? And if yes, then what is going to be the regular expression of L? Now obviously I can just give you the answer right here, write the answer here, and it's all done. But first of all, that's boring, and second of all, from this course I don't really want you guys to learn a lot of solutions. I don't even want you to learn a lot of algorithms that will get you the solutions. Instead, what I really want you to learn is how to think. When you are given a problem, I want you to build the skill of approaching that problem in a systematic way, to build up a solution from scratch step by step. So let's do that right here. We are dealing with binary strings here. So let's look at what we know about binary strings. First of all, binary strings are made of 0 or 1, right? And the length of a binary string can be anything. There is no restriction on the length, so the length cannot be 0. When the length of a string is 0, that's just the empty string epsilon, and this is not a binary string. So the length can be 1 and higher, so 1, 2, 3 to infinite. And at each of those positions, we can have either 0 or 1. So we can have a 0 or 1 here. We can have a 0 or 1 here. We can have a 0 or 1 here, and so on. It can have a length of 1, it can have a length of 2, 3, it can have a length of 2563. So what we are getting here is one or more occurrences of this term, right? Do you remember the term one or more occurrences of something? Exactly, that's the positive closure. So I'm taking a positive closure of what? This term, 0 or 1. So I'm saying that I will take a 0 or a 1 as many times as I want, starting from 1 and ending with infinite. So this is the expression of this language. And as we have a regular expression for this language, we can say that the language is regular. Now, does that make sense? I hope it does. Let's move on. We have another language here in our second example, and for some reason we are still calling it L. So the language L has a lot of strings. This is another infinite string. A side note here, every finite string is by default a regular language. Why? Well, I'm gonna leave it to you guys to find out the answer to that question. If you can't, I will give you the answer someday in the future if I'm still alive, and if not, well, sad. Anyway, so this language has the strings A, double A, triple A, quadruple A, a lot of A's. Also AB, 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 you get the picture. So when we are looking at this language, what is the pattern that you can see? Well, in fact, this language has not one but two different patterns. First of all, we have a repetition of A's, right? So I have A, and if I take it one time, it's still in the language. If I take it 0 times, I will get epsilon, which is not in the language, and therefore I cannot take A 0 times. I have to take A at least one time. If I take A 2 times, I still have the string in the language. If I take A 3 times, still in the language, and so on. So we have another case of one or more occurrences of A, right? So this is another positive closure. This pattern covers all the strings from here to here, but these are different, right? These are not a repetition of A. These are a repetition of what? AB, right? So we have A, B, and again one or more repetition of AB, so a positive closure of that. So we can have either this or this. So we have one or more A. If the string is made of one or more A, the string matches with this expression and the string will be in this language. If the string is made of one or more repetition of the string AB, that will match with this expression as well, and that string will also be a part of this language. So our two conditions are being satisfied, so we can say the expression for this language is this expression. Okay, cool. We are going to move on now. Okay, so for the following examples, just assume that the alphabet is going to be 0 and 1, which means from now on in this lecture, we are only going to deal with binary strings. So this is our first example. And in this example, we have to find an expression for a language, and that language is the language of all binary strings with one additional constraint, and that is the binary strings are going to have to start with 0, right? So let's start with all binary strings. We have all binary strings, that is 0 or 1, positive closure. We just saw this a few minutes ago. So this shouldn't work, right? Yes, we can create any binary string that starts with 1 with this expression as well, but all the strings that can be created using this expression are not going to be in this language. So one of the conditions is being violated. So this is not going to work. So what is the modification? Well, let's look at the limitation of this expression. This expression is telling us that in every position of that string, you can have a 0 or 1, right? A 0 or 1 here, a 0 or 1 here, 0 or 1 here, and so on. But what is this example telling us? The example is telling us that the first position has to be 0. It cannot be 1. This part, still one or more repetition of 0 or 1, and this is a 0. So we have 0 concatenated with 0 or 1 closure. Is that correct? Well, almost, but not quite, because now that we have established that the first symbol is going to be 0, so we can have an empty string from here. Now that we have made sure that the first symbol is coming from here, we can have an empty string from the rest of it, because otherwise this string, this language contains the string 0, right? Because 0 is a binary string and it starts with 0. So this string, the string 0, is in this language. But if we put a positive closure here, which means I'm going to get a 0 from this symbol, and I have to have a 0 or 1 from here, because this is at least 1 occurrences. So I will have at least one of this, which is giving me a total length of 2. Where is our 0? So the string 0 does not match with this expression, and that is a violation of one of our conditions. Every string that is in the language must match with this expression. So what can we do? We can just make it the link closure, which will allow us to take none of this, and that will give us the string 0, which is of length 1. So what is our answer? The answer is first symbol is going to be 0, and then we can have something, we may not have something. So if we have something, that will be either 0 or 1. Take it as many times as you want. If you don't want to take it, then don't take it. So this is our expression for this language. So moving on with our next example here. This is pretty similar to the last one, but instead of starting with 0, now our binary strings want to end with 2 consecutive ones. So let's say this is our binary string. What we are saying is that the last 2 symbol is going to be 2 ones. Now the question is, what can we have in this place? Well, we can have a lot of things, but all of those things has to be created using these 2 symbols, either 0 or 1. We must also have epsilon, because the string 11 itself is still valid, because it is a binary string that ends with 2 consecutive ones. So even if we don't get anything in here, the string must still match with the expression. So combining all that logic, we get our answer. The last 2 symbol is going to be 1 and 1, and before that we can have anything made with 0 or 1. We can get a 0 or 1 here. How many times? As many times as we want, including 0 times. So this is just a link closure. This is pretty similar, because let's see here, we have 0 or 1 whole star, but we have a 0 before because the string is starting with 0. We want to ensure that this is similar, 0 or 1 whole star, but a double 1 at the end, because we want to make sure that the string is ending with 2 consecutive ones. I hope that makes sense. Okay, so next question.